You've probably seen those incredible pictures of massive dams. They're just amazing feats of human engineering. But have you ever stopped to wonder how they actually get built? Well, today we're going to pull back the curtain and go deep inside the super complex world of hydropower engineering, all the way from a raging river to the quiet electricity powering your home.
I mean, look at this. Structures like these are basically modern-day colossi, a huge testament to what we can build. But they don't just spring up out of nowhere. Nope, they are the result of just immense, meticulous planning and precision. So, how does an idea on a piece of paper become this? A concrete, power-generating reality? That's the big question we're going to tackle.
So here's our roadmap for today. We'll kick things off with the raw power of water itself. Then we'll move into how you even begin to design one of these things. After that, we'll dive right into the core engineering, the real nitty-gritty. Then we'll see how it all gets put together, and finally, what it all means for our energy future. Okay, so first things first, why on earth go to all this trouble? Well, the very first step is really understanding the immense force that we're dealing with. It all comes down to taming one of the most powerful, most relentless forces on our entire planet, water. This image right here, this captures the entire point of the exercise. You are taking the immense, kind of chaotic energy of a river, and you are channeling it, converting all that raw kinetic force into the steady, reliable electricity that powers our world. Right, so before a single shovel ever hits the ground, an unbelievable amount of intellectual heavy lifting has to happen. Honestly, this is where a project is won or lost. It's all in the planning. To manage a project of this insane scale, the industry often uses what's called an EPC model. That stands for engineering, procurement, and construction. The easiest way to think about it is like a master key. One single contractor takes full responsibility for the whole shebang, from the very first sketch to the final switch on. It's the only way to streamline a process this unbelievably complex. And this approach is absolutely crucial because you've got all these different teams of specialists, geologists, structural engineers, electricians, and they all have to work together perfectly. Every single component, from a tiny little sensor to the massive dam wall itself, has to function in perfect harmony. No exceptions. Okay, now let's get into the build itself. This is the fun part. We can really break down the core engineering work into 3 essential pillars. This is where the magic really happens. To build a modern colossus like this, you need total mastery in 3 distinct but deeply interconnected fields of engineering. So let's take a look at each one. First up, we have civil engineering. If the dam is a giant, then this is its skeleton. The civil engineers are the ones responsible for the massive, immovable structures, the dam itself, the spillways that handle any overflow, and the very foundation that it all sits on. And believe me, it is so much more than just pouring concrete. These folks are performing intense structural analysis to make sure the dam can withstand earthquakes and geotechnical analysis of the rock underneath to be positive it can support that unimaginable weight. It is all about long-term stability and safety. Next, we have mechanical engineering. So if civil engineering provides the bones, this is the muscle. These are all the moving parts that actually harness the water's power. The giant pipes known as penstocks, the massive valves and gates, and of course, the turbines. And here's something you might not know. Not all turbines are created equal. Engineers have to choose the perfect one based on the site's head, which is basically just a fancy term for how far the water falls. Got a very high, steep drop creating immense pressure? That's a job for a Pelton turbine. A lower dam, but with a huge volume of water? Well, a Kaplan turbine is way more efficient. It's all about fitting the right tool to the landscape. But ultimately, everything, all of that planning, funnels down to this, the turbine. You can absolutely think of it as the heart of the entire operation. This is the one precise point where the incredible force of moving water gets converted into mechanical rotational energy. And finally, that brings us to our third pillar, electrical engineering. This is the brain and the nervous system of the entire plant. It's the part that takes that spinning energy from the turbine and generator and turns it into electricity, and then controls it and distributes it safely. This means they're designing the whole powerhouse, creating complex protection systems to prevent any failures, and integrating what are called SCADA systems. That's just the tech that lets them monitor and control everything remotely. And maybe most importantly, it handles the connection to the national grid. I mean, after all, the power is pretty useless if it can't get to our homes, right? So we have our three pillars of engineering: the bones, the muscles, the brain. But how do you coordinate all of this into a real-world project that takes years and years to finish? Well, that's where project management comes in. The whole life cycle follows a really clear path. It all starts with feasibility studies, basically asking, is this even a good spot for a dam? Then comes the very long process of getting all the permits. Only then does construction actually begin. And that's followed by intense testing to make sure everything works perfectly. And finally, a long-term plan for operations and maintenance gets put into place for the decades to come. And then there's the just unbelievable challenge of logistics. Seriously, stop and imagine this for a second. Imagine sourcing a custom-built, multi-ton turbine from a manufacturer halfway across the world. Now imagine having to transport it over oceans, through mountains, to a super remote construction site, and getting it there on time and in perfect condition. It is a monumental task of global coordination. So, after all that planning, all that mind-bending engineering, and all that construction, what have we actually achieved? Let's zoom back out for a second. Because the end result isn't just a dam. It's not just a wall of concrete. It's a source of clean, renewable energy that can power communities for generations. It represents the ultimate payoff, transforming our natural world not by conquering it, but by working with it to build a more sustainable future. And that leaves us with a final thought to chew on. These projects are massive, they're complex, and they take years to build. But as our global demand for clean, reliable energy just continues to grow and grow, what role will these modern colossi play in meeting that demand and powering our future? It's a pretty big question we're thinking about.